This is problem 26 of the QHack 2023 Quantum Coding Challenges, and this one is entitled Don't Hit the Ground. Now, in this problem, what we're being asked to do is to simulate the effect that a thermal environment has on a qubit. And we're told that we can somewhat accurately do this by using what is known as a generalized amplitude damping channel. And that if we have access to this model and we pass to it a parameter gamma times some time delta t, where gamma is the photon loss rate at zero temperature, and then delta t is just a small period of time, and then we also pass some probability p, which is the probability that a qubit can emit a photon. So if we have that available and we repeat this many times, we can model the effect that this thermal environment has on a qubit for after some time t. Now, there are a couple of ways we can solve this problem. We can solve it analytically, or we can use the generalized amplitude damping channel available in Penny Lane and then implement this circuit with many repetitions. So let's go ahead and take a look and see how we can do either of these two approaches. So first, the generalized amplitude damping channel is a map that takes as an input some density matrix rho and then applies the summation of this cross operators k sub I given by these four matrices here. Now, from this representation here, it might be somewhat difficult to understand what this map is doing. So let's go ahead and take a look and see what happens when we apply it to an arbitrary density matrix rho. So if we have the density matrix rho in the block form given here, if we apply this map, what we end up having is that for the off-diagonal terms, we have them multiplied now by this square root of 1 minus gamma. So we can see here that as gamma increases, so this photon loss rate gets higher, our off-diagonal terms are going to decrease. So basically we're going to experience some dephasing, so turning a coherent state into a mixed state. And then if we look at the diagonal terms, what we see here is that because we have this plus term here and this minus term here, as we change this value of gamma and p, one of the diagonal terms is going to increase, the other diagonal term is going to decrease. So we're basically shifting the probability from one possible output state to the other. So for example, for a positive value of gamma, we're going to see that the probability of occurrence of the zero state, which is this first term here, right, is going to increase, and the probability of occurrence of the one state is going to decrease. So basically, this is representing that if we start with some sort of coherent superposition state, that state is going to start moving closer and closer to our zero or ground state, or what they call it here, the fiducial state of our system. Now, this is after the application of this map one time, but what we want to do is apply this many times to simulate the effect of a thermal bath. So if we were to apply this map n times, what we're going to see is that these off-diagonal terms are going to decrease exponentially with n, and then the diagonal terms are going to have this factor that also decreases exponentially with n, and then this constant multiplied by this polynomial on gamma, which is just basically this geometric series of 1 minus gamma to a power of I, where we're summing up to n. So this function f of gamma, for n large enough, it's going to be basically 1 over gamma. Now, what we're being asked to do in this problem is to take a look and see what happens when we apply this map many times to the starting state plus, so an equal superposition of 0 and 1. So if we look at the density matrix of this state plus, we have 1/2 of 1, 1, 1, 1. So that means that the probability of measuring state 1 is 1/2, right? So this is the probability of measuring state 0. This is the probability of measuring state 1. And what we're asked is find the value of time t for when this probability of 1/2 turns into 1/4, which is the relaxation half-life. So what that means is that what we want to find is when this term here, which is the probability of measuring 1. So if we go up here to this matrix, right, this term right here is the probability of measuring state 1. So that's exactly what we have down here. We want to find when that is exactly equal to 1/4. But if we're going to do this in small steps of time, we want to find when this is at least smaller than 1/4. So we can now simplify this a little bit by seeing that this z is equal to 0, right? This is the general expression for a density matrix, right? And if the density matrix of the state plus has a 1 here and a 1 here, the only way we get this is by making this z equal to 0, right? So if we plug in 0 in this expression, we can solve and find that for this f of gamma, which is that geometric series we have here, we need to find the n such as that sum is greater or equal than 1 over 2 gamma times 2p minus 1. So that's it. So what we can do is programmatically find this 1 minus gamma to the power of 0, then check if it's still smaller than this value, and then add to that 1 minus gamma to the power of 1, check again, and then keep going on and on to each power until we find when this is greater or equal than this expression. Now, since we're doing this in small steps, this gamma is actually delta t times the gamma value that is going to be given to us in our problem, and same here is delta t times the gamma that is given in our problem. So all we need to do is just code this up. So here I'm going to be importing PennyLane and NumPy. I know that this approach we just described doesn't use PennyLane, but we'll look into it using that generalized amplitude damping block within PennyLane in a minute. So let's do that import. And then all we need to do here is define a function half-life that takes as an input gamma and the probability p. And we're going to define some small delta t, let's say 0.0001, for example. Then n, which is the number of times we're going to apply that generalized amplitude damping channel. So we're going to start that at 0. And then f is going to be that geometric series function that we're going to start adding terms as we increase n. And what we need to check is that while f is smaller than 1 over 2 times delta t times gamma times 2p minus 1, right? That's what we derived. We need to now do f plus equal 1 minus delta t times gamma to the power of n, right? And then we do n plus equal 1. And then we just return delta t times n, right? So delta t is the time step, and then n, the number of times we've repeated this. So that gives us the total time at which we reach that relaxation halftime. Okay, and then we're given these two values of gamma and p as inputs. So then if we just call this function for those two values, we see here we get 9.0446, which if we look at the results here, it's close to what is given as an answer. And then if we use this second input, we're supposed to get 7.09, which if we run it for that, we get 7.085. Okay, now the other way we can do this is by using PennyLane's generalized amplitude damping channel. So we're going to define this function again, half-life, and then we're going to define a device, and we have to use the default mix device for this one because we're going to be working with mixed states. Then we define our Q node, which we're going to call noise. It's going to take us an input gamma, p, that delta t, and then n is the number of times we're going to apply the depolarizing channel. And then the first thing we need to do is initialize our state applying a Hadamard gate, right, to implement that equal superposition. And then we need to apply that depolarizing channel a number of n times. So we're going to do it in a for loop. And then that channel takes as an input gamma, which in our case is the gamma that's given to us times delta t and the probability p, and then on wires 0. And then here, what we need to do is return the probabilities. Now we're going to do something similar to what we did above. We're going to define some delta t. Here I'm going to use a larger value because here we're going to have to apply many times this depolarizing channel with this for loop. So the smaller the t, the more times we need to apply that gate. And then one thing we could do here is just do a for loop in which we start increasing our number of steps little by little, but that will take a really long time. So a better approach is to start with some minimum time, which here is 0, and then we specify some large number for the maximum time that we think this might take. So let's say, I don't know, 100. And what we do here is we can do binary search. So we can just look at the first half between this Tmin and Tmax, see if our result is there. If it is, then start cutting that time in half until we converge to the final time. So we do that by doing a while loop where our Tmax minus Tmin is greater than our delta t. And then we define a Tmid, so the mid value that is going to be between those Tmax and Tmin, and then calculate our probability by calling this noise Q node where we're going to pass the number of steps as the integer value of this Tmid divided by our delta t. And then since this returns the probability of measuring both 0 and 1, we need to take just the probability of measuring 1 and check if what we measured is larger than a quarter. And if it is, we define this new Tmin as our Tmid. So we're going to be searching now on the second half of that time range. But if not, then we define our new Tmax as Tmid. So we're going to search now on the first half of that time range we have. And then this overall function needs to return Tmid, which at the end will converge to the value we're looking for. So if we now come up here and run this function for, let's do it for this second input, which was 7.085. It's what we got with our first approach. And here we forgot to define this variable numWires, which was given in the problem, and that's just 1. So I'm gonna just replace it there for 1. And then here I misspelled Hadamard. Okay. Then we run that. It's gonna take a little while because we're applying all those gates many times. Okay, and after a minute or so, we get 7.0854, which is very close to what we had with the analytical approach. And then let's try that for that first input that's given to us. And again, after a minute or two of waiting, we get 9.044, which also was very close to what we got with this one. Let's just run it again, since that one runs pretty quickly, to confirm. So 9.0446 and 9.0446. So I hope this was helpful, but as always, let me know if you have any questions.